Okay, so this is our first video of section 5. We're looking at isometries and orthogonal matrices. Let's start with definition. An isometry called, which we'll denote by T for the moment, which is a map which will take Rn to Rn, is a distance-preserving map. So, what we mean is that if I take any two vectors x and y, these are going to be vectors in Rn. T of x is the vector, is also a vector in Rn. The length, the magnitude of the vector t of x minus t of y is the same as the length of x minus y. And that's going to be true for all x and y vectors in Rn. So that's what we mean by an isometry. Take the length between any two vectors, the image of those vectors under this map, the length between those is the same. Worth pausing for a minute. For one, just the word itself is made up of iso, which means same, and metri, so metric, which is length, so same length. This is a really important type of map, distance preserving. So maps that don't change the length, we can think of these as maps that don't distort. Okay, so it's a really important concept that we'll see a lot through the rest of the course. Just to think of some simple examples. Rotations, reflections, translations. These are the most obvious intuitive isometries. So you might think about if you want a very physical example, consider throwing a rock in the air. Okay. Now what I can imagine doing if I wanted to describe the motion of that rock, so suppose this is my rock, and maybe I give myself a coordinate system, and maybe this is the rock at time t equals 0, and so I could describe the rock by, say, all the points, a continuum of points inside the rock. So maybe this is, I won't draw the arrows, but maybe this is point x in the rock, and this is point y in the rock, and as the rock is flying through the air, obviously these vectors are changing, and so maybe if I look at a different time, that's a bit hard to draw because that shape is the same, which is the point. So maybe at a different time it looks something like this, where this is, say, x, and this is y here. And we could imagine describing this motion by a map t, which is going to be a different map for every point in time little t. But the point is that because this rock is what is called a rigid body, which is a concept you'll get into in the dynamics course next term, but you can certainly appreciate that the distance, if I take any two vectors inside the rock, the x and the y here, then this distance between them is not changing throughout the motion, right? In fact, this motion consists of a rotation. The rock rotates and the rock undergoes translation as it flies through the air. Okay. So let's push a little bit further on rotations and reflections. One question we might ask is, can we describe such a map, such an isometric map, with a matrix. Matrix multiplication is also a map from vector space to the same vector, well, map from vector space to vector space. Let's do this in R2, and we'll generalize this to R3 later. And we'll start with rotations. Rotations about the origin by a given angle theta. In fact, we encountered this idea at the end of our section on conics, but now we're going to make this a little bit more rigorous and formal. So, what I mean is I take a vector v in the xy plane, and I want to rotate that vector about the origin by angle theta. So that's taking this vector, rotating it this way by angle theta, and not changing its length. So if that's vector v, I want to imagine the map which takes v to, let's call this r theta v. So I'm denoting the map by r theta. So this is the image of that map. And I say, how do I describe that map? Well, it's a rotation. You might be inclined to think about polar coordinates. In polar coordinates, if I define v by its length and its angle off the x-axis, so let's call that angle alpha, and I won't draw it here, but let little r be the length of that vector, then I can write v as x equals r cosine theta and y equals r cosine alpha and y equals r sine alpha. In fact, if you haven't encountered polar coordinates yet, don't even worry about that. This is just the trigonometry of this triangle here. So that's a generic representation in terms of a radius and an angle of a point in the plane. And under this map, that point transforms to, well, all I'm doing under this map, this is why this is a useful coordinate system, is changing the angle. I'm not changing the length, I'm only increasing the angle by an amount theta. So this transforms to the vector r theta v, which is, in this system, r cosine alpha plus theta, r sine alpha plus theta. Right, again, all I've done under the map is increase the angle by an amount theta. Okay, so now what you can do is take this and expand using trig identities. This cosine and sine of a sum, and doing that, you can write this as r cosine theta cosine alpha minus sine theta sine alpha, and sine of a sum expands as cosine theta sine alpha plus sine theta, cosine alpha. Okay. And what I really want to do, when I say can I describe this by a matrix, what I want to be able to write is r theta v equals some matrix times the vector v. So I'm looking to extract vector v out of this, which is r cosine theta, r sine alpha. And so the key is to rearrange this a little bit as a matrix times a vector. So if you see I have an r cosine theta and an r cosine alpha and an r sine alpha here, in all of these terms. So if I write this as cosine theta minus sine theta, this should be cosine theta sine alpha. This is a theta here. So, but I want to extract the cosine, r cosine alpha, so I'm going to write this as, call it a sine theta and cosine theta times the vector r cosine alpha r sine alpha. Okay, so you can verify going the other direction that this matrix times this vector is the vector here. Again, the point of writing it that way is that I can view this r theta v as this matrix times r cosine alpha r sine alpha, which is v itself. So we could define this matrix to be, okay, a bit messy on the notation. Here I'm talking about the map, and here I'm showing that that map is equivalent to multiplication by this matrix, and I'm being a bit naughty by giving that matrix the exact same name as the map, but that's okay because we're going to use this a lot. So call that matrix r theta v, or sorry, call that matrix r theta, which is independent of v, and therefore I see that this map is equivalent to the matrix r theta times the vector v. Okay, so in other words, for any v, the multiplication by r theta v, multiply by r theta, and you get a matrix which is the rotation of v by angle theta in the counterclockwise direction. That's for theta positive. Theta negative, the map is still works. Theta negative is just rotation in the clockwise direction. Okay. Let's have a look at reflections. And again, if you went back to what we did at the end of section 4 on conics, you'll see that we used that map in getting to the normal form for an equation of an ellipse, or generically to transform degree 2 equations. This is the this is the derivation that goes along with that. Okay. Next one we'll think about is reflection about a line, and we'll think about the particular, we'll give the line the form y equals tangent theta x. So I'm thinking about the map. So here's an angle theta. I'm thinking about the map that takes any point and reflects it across that line. And by reflect across the line, it means we go to the line orthogonally, we go through the line by the same amounts, and that's where we end up. So if this is vector v, then I'm looking at the map that takes v to, I'm going to call it s theta v. That's my reflected image of the points through the map. Okay, so to make some sense of this map, let's define v by its coordinates x, y, and in fact, though it doesn't look like this has anything to do with angles necessarily, in fact, angles are the useful way to think of this map. And so let me again write this in its polar form, r cosine alpha, r sine alpha. So here's angle alpha. The observation that's useful here is that what are we doing in this map? This is the image. So the line I'm defining by angle theta, and therefore this angle here is theta minus alpha. And by the symmetry properties of this reflection, this angle here is also theta minus alpha. So this vector v, what I'm really doing is changing its angle by adding theta minus alpha, 2 copies of theta minus alpha to the angle. And I'm not changing its length. So s theta v is the vector which has polar representation, the same r, so I don't change its length, and cosine, well, I started at angle alpha, and I add 2 theta minus 2 alpha, which means I end up at the angle 2 theta minus alpha. And similar, the y-coordinate is just going to be the sine of that. Okay, do a similar trick. We've got a cosine and a sine of, in this case, a difference. Apply standard trig identities to that. I'm going to sort of jump straight to the punchline. I expand that, and I try to sort of, if you want to think, factor out r cosine alpha, r sine alpha, and you can write that as the multiplication of the vector, or sorry, the matrix cosine 2 theta, sine 2 theta, sine 2 theta minus cosine 2 theta times this vector v, r cosine alpha, r sine alpha. And again, we'll define this as the matrix s theta. And so this reflection map is equivalent to multiplication by the matrix s theta times NEV. It's probably worth noting this is not the same form. Right, so you might, a reflection is not a rotation. Right? While these look similar, this form cosine minus sine, sine cosine, is not the same as this. Here I've got cosine and a minus cosine with positive on the signs. Okay, so worth getting used to those differences. This is the form for reflection by across this line with slope defined by angle theta. Now, worth noting that this problem, this idea of reflection, is harder if the line doesn't pass through the origin. So, to see that by an example, this is example 61 in the online notes. Let's consider reflection about the line x plus y equals 2. Okay, so let's draw a picture. X, y, 1, 2, 1, 2. Here's my line. Y equals 2 minus x. The map itself is defined in the same way. Take a point on either side of the line. Its image under the map is defined in the same way. But this is not a line. The idea we've derived up here is not going to work because I can't play this game with angles, right? Because this line does not go through the origin. Well, you might say, well, okay, it's not so different. what I can do is shift my origin so that I do get to that case, work out how the map looks in that shifted coordinate system, and then shift back. And so to do that, what we do is step one is shift our coordinates. So let's define, all I need to do is move my origin 2 to the right, or I could move 2 up if I wanted. Let's move 2 to the right. So I'm going to define x hat as x minus 2, and y hat will keep y hat equals y. And so picture is now, I'm defining a new coordinate system, which we'll draw in red. There's y hat. And, well, x hat is still going that way, but now here's the origin. And in that new coordinate system, the line is through the origin. Yeah, in fact, that line, because this was a slope of -1, this is pi over 4, or really minus pi over 4. And so that line is the line y hat equals minus x hat, which we could write as tangent of minus pi over 4 x hat. And so s theta, let's call it s theta hat, that's the matrix representing that reflection in the hat variables, is, we just read it off, put theta equals minus pi over 4 in the form up here. The cosines go away because those become cosines of minus pi over 2, so zeros on the diagonal, and sines of minus pi over 2 on the off diagonal. So we get 0 minus 1 minus 1, 0. Okay? But what I really want is to describe that map in my variables x, y, so we need to say, well, how do I sort of unshift? Well, the first thing we can do is write this in a slightly different way. So using this notation that as maps to, so x hat, y hat maps to 0, minus 1, minus 1, 0, x hat, y hat. That's true for any x hat, y hat. And to define the map in the original variables, to sort of unshift, I need to go back to this definition here, and I'll keep this in this. I'll keep doing this computation with this notation. So x hat, y hat is xy minus 2, 0. So we could say that xy minus 2, 0 maps to, that's the left-hand side, maps to this matrix times x hat, y hat, which is the same as that matrix times x minus 2y. And matrix multiplication times a sum, I can expand. So that's 0, minus 1, minus 1, 0, xy, and minus 0, minus 1, minus 1, 0, 2, 0. So all I've done is replace the x hat, y hats with x minus 2y, which I've written as the sum difference of two vectors, and expanded this, this matrix here with that difference. So now we look at that, and well, I can simplify this, or multiply that out, and if you do that, you get the vector 0, minus 2, and the last thing is that if xy minus 2, 0 maps to this thing minus this thing, then xy maps to all of that right-hand side plus 2, 0. So therefore, xy maps to, so I take, this is minus 0, minus 2, and I'm going to add 2, 0. And so that is the vector 2, 2 plus this. 0, minus 1, 0, xy. Okay. So, a couple of quick observations. In this case, reflecting about a line that did not go through the origin, it is not possible to write that map as a simple matrix multiplication. So, what we end up with is that, so this is the definition of the map, if you wanted. The map takes xy to this matrix times xy plus this vector. Okay, so it's matrix multiplication plus a constant vector. Okay, so in the last video we defined these maps r theta and r theta and s theta, which represented rotations and reflections in R2. And our intuition tells us that these are symmetries by the fact that there's no change in length when you map something by a reflection or a rotation. But let's verify that by the definition. So I want to check that the maps r theta, s theta, for which we defined matrices, do these define isometries? So we need to check. Let's focus on the r theta. What we want is that r theta u minus r theta v is u minus v for any u and v. Okay. Well, since this is just multiplication by a matrix, I can write r theta u minus r theta v as r theta u minus v. And so that is equal to magnitude u minus v for all u and v if r theta x is magnitude x for all x. All right, so I don't really need to worry about two vectors. If I can show that this distance holds for any vector x, then I get an isometry. Well, let's let x be xy. Recall that r theta was the matrix cosine theta minus sine theta, sine theta, cosine theta. And so if I take magnitude of r theta x squared, then I get cosine, the x component is cosine theta x minus sine theta y, so I get cos theta x minus sine theta y squared, plus the y components, which is sine theta x plus cosine theta y. Squared. And now we can expand that and we get some various trig identities. So I get a cosine squared plus sine squared times an x, and the similar for a y, and my cross terms cancel out, so I'm left with just x squared plus y squared, which is what I wanted, which that is magnitude x squared. Okay, I want to do the calculation here, but it's a very similar calculation for s theta. Right, so that verifies that those maps are indeed isometries. The question we might ask is, what other, so these are particular maps that could be represented by multiplication by a matrix. What other maps, multiplication by a matrix, can be isometries? So let's ask the question. Let A be an n by n matrix. And I want to know what needs to be true about A when is the map V to AV an isometry. Okay, for which matrices A is this matrix multiplication in isometric map. Okay, so first, it's useful to make a note about angles. So let T be an isometry, and let's consider for the moment an isometry that fixes the origin. So what I mean is that T of 0 vector is the 0 vector. We'll relax that restriction a bit later. But for now, consider such isometries. And the claim is that an isometry also is angle preserving. So to see that, we consider Tx minus Ty magnitude squared. We can expand that as magnitude Tx squared minus 2 times the dot product of Tx and Ty plus a magnitude of Ty squared. By virtue of being an isometry, this is equal to magnitude x minus y squared. That's by isometry. And I could expand x minus y squared as magnitude x squared minus 2 x dot y plus magnitude y squared. Okay, but it's also the case that magnitude Tx is magnitude x. And you can see that by going back to the definition of isometry and setting y equal to the 0 vector and using that the isometry fixes the origin. So preserves the length of any individual vector, similar to what we were doing in the calculation up there. And magnitude of Ty is equal to magnitude y. And so in this expression here, these cancel, those cancel, and what we're left with is the conclusion Tx dot Ty equals x dot y. Okay, so at least an origin fixing isometry is also angle preserving. Okay. Now, let's consider matrices, n by n matrices. And the claim then is that we should, if we're seeking to classify all possible matrices that are isometries, what we should do is we want to seek A such that AV.AW is V.W. In other words, this angle-preserving view of isometry is going to be more useful in classifying the A and for all V and W in Rn. If you want to verify that that is going to give us isometries for A, you might note that if we take V equals W, we see that any A that satisfies this is going to be length preserving, because it's magnitude of AV on the left and squared, and magnitude of V squared on the right. it is angle preserving by the simple statement that AV.AW is magnitude AV magnitude AW cosine theta. Right, so that says this is angle preserving and, well, length preserving of a single vector. We could, of course, also write that AV minus AW is AV minus W. Again, applying similar operation. And so it's not just length preserving of a single vector, but of the difference of two vectors. Okay, so that's the statements that we want to work with. AV.AW equals V.W. And now a sort of trick is for V and W in Rn, we can write the dot product V.W as the sum of the multiplication of the components, right? The sum of the little v sub i's times the w sub i's, I equals 1 to n, which is the same as writing a row vector v1 to vn times the column vector w1 to wn. Okay. So thus far in the course, we haven't been paying too much attention to writing, we haven't been worrying too much about writing a vector as a row vector or a column vector. When we're multiplying with matrices, we really think of vectors as being column vectors. So here when I mean all of v and w and Rn, I'm really thinking of these as being column vectors, so that matrix multiplication occurs in the way we're used to. And therefore this expression here, v's times the w's, this is really the transpose of v. So we would write this as v transpose w. Okay, so playing with this expression, AV.AW, I can write as the transpose of the column vector AV, AV transpose times the column vector AW, and now we can use properties of the transpose, which I won't derive here, but are easily enough shown to be true in linear algebra, which is that the transpose of a product is the product of the transposes, but with the order flipped. And so this is V transpose, A transpose, AW. I might pause. So normally when you're writing, when you're expressing, when you're talking about the vector, we'd have some notation as I've been using the little squiggly, whereas when we're writing it in this form, it's usually expressed slightly differently. So it might be better to write these without the squiggles. So in the typed notes, you'll always see there's a slight difference between this will be, say, boldface, and this would not be boldface. So let me try to have such a notation here. So V transpose A transpose AW, and there's also a property where we can switch the order of these operations, and so I can write this as V transpose A transpose AW, and get rid of the parentheses, and that equals, well, let's do the other side, V dot W, we just said is V transpose W, and so these are equal if A transpose A is identity. Okay. That is, AV dot AW is V dot W for all V and W, if and only if A transpose A is the identity. And that's, if these are vectors in Rn, then that's the n-dimensional identity matrix. So by the calculation we just went through, you might be questioning this if and only if a little bit. The calculation we just went through is really proving this direction. If A transpose A is identity, then those products work out exactly the same. If you wanted to be convinced of the other direction, that this implies A transpose A is identity, I won't go through a full proof, I'll just outline an idea. So if you, for instance, took V to be, say, 1, 0, 0, or E1 if you want, and W similarly to be 1, 0, 0, then of course V dot W is 1, and AV dot AW said V transpose ATAW. Well, this is just some, think about it in terms of multiplication, this is some matrix M. V transpose MW in this case would be 1 with lots of zeros times M times 1 and lots of zeros, and that would just pluck off the 1, 1 component of M in the case where those were 1, 1, 0, 0, 1, 0, 0. So that would be what we might call M11. Which shows that the 1, 1 component of A transpose A is 1. If we then took, say, W equals putting a 1 somewhere else, we could pull off all of the components of M, and you would see that you get 1s down the diagonal and 0s everywhere else. So this is an if and only if. As a definition, a real square matrix A is called orthogonal if A transpose A is the n by n identity matrix, i.e. A inverse is A transpose. All right, so matrices that satisfy A transpose A equals identity are called orthogonal, and these are strongly connected to isometries in a way that we've hinted at here. So, basically what this proves is that an orthogonal matrix is an isometry, and an isometry which is made up of a matrix multiplication, that isometry requires an orthogonal matrix. Okay. So then the question is, are those all isometries? And it's not quite the case. So if I take a vector V in Rn, a linear map V to TV can be represented by a matrix, i.e. T of V is some matrix A times V. Right? What I'm getting at here is we might have isometries that are not multiplication by a matrix. If we're thinking of matrix multiplication, we require an orthogonal matrix. So now we're sort of trying to classify maps in terms of whether I can represent them by a matrix, and this statement says that if the map is linear, then it can be represented by a matrix, and if it's an isometry, then furthermore it's going to have to be an orthogonal matrix. So that means that all linear isometries of Rn have the form of a matrix multiplication for some matrix A with that matrix A orthogonal. Okay, let's push this idea a little bit further. Well, coming back to the statement, a linear map can be represented by a matrix. To convince ourselves that that is true, so if T is linear, then that means that T of alpha A plus, say, beta B can be written as T alpha T of A plus beta T of B. And thus, if I apply T, well, take any vector V, and let's suppose V can be written with components V1 up to Vn in the standard basis E1 to En, then T of V, by the linearity of the map T, can be written as the sum of the V sub i's times T applied to the E sub i's from 1 to N. And that is equivalent to taking the matrix made of column vectors TE1, TE2, and so on, TEN, times vector V. Right, so whatever T does to those basis vectors, I put those in the columns of the matrix, and you can sort of imagine this working. If you multiply this out, you're always getting the elements of this first column multiplying V1, which is evident here in the V1 times T of E1, and so on. Okay, so this is sort of a useful way of expressing matrix multiplication times a vector. And that says that any linear map can be represented by a matrix, and this is the matrix representation of that map. This is an idea that we will touch on some more in coming videos. That gives us a quick, at least pseudo-proof of the equivalence between a linear map and representation by a matrix. Final point is that to the question of whether there are other isometries, there are. So consider this map. T of V is A, V plus B, so B being a fixed vector in Rn, and A being orthogonal, so ATA equals identity. So this is the map here, TV, multiplication by an orthogonal matrix, but then plus a constant vector B, which is like just a shift. Right. My claim is that this is also an isometry. But this is not linear. The fact that this is not linear is evident from applying this definition of linearity. T of a sum, say x, just do an x plus y, is ax plus y plus b. I can now expand the matrix multiplication. I get ax plus ay plus b, which is not the same as what I get when I apply t to x and add t to y, because this would be ax plus b plus ax plus b. I would have 2 copies of b, whereas I only have 1 here. Okay. This is really going back to the origin fixing. Right, a lot of these statements were starting from an origin fixing map. Such an isometry like this, multiplication by matrix, is always going to be origin fixing. This is not origin fixing because I have this shift b. Okay. But we can check that it is in fact an isometry. Tx minus ty, which goes straight to the definition, is a x plus b minus a y plus b. The b's disappear, and we're just left with the magnitude of ax minus ay. And since A is an orthogonal matrix, that does satisfy distance preserving, length preserving equals x minus y. Okay, so to summarize, we're making this connection between general isometries and matrix multiplication. If I have a map defined by matrix multiplication for it to be an isometry, that matrix has to be orthogonal. There are other isometries which involve multiplication by an orthogonal matrix, but which are not linear. And this is an example where we just shift by a vector b. What we'll show at the very end of this section is that there are no others. So in fact, all isometries have this form of representation. Orthogonal matrix multiplication plus a constant shift.